I'm Gabriel Pasquale, and I'm the lead instructor for embedded security and hardware hacking. In today's distributed computing environment, the ability to update software after it has been shipped to the user is critical. Medical devices, consumer electronics, and self-driving cars are only a few examples of systems that require the ability for companies to remotely fix bugs, add new functionality, and patch security vulnerabilities. Unfortunately, remote software updating doesn't solve everything, and even creates its own set of security concerns because of added complexity. Bad actors may try to read the updates in order to steal or reverse engineer precious intellectual property, modify the updates to insert malicious code, which could cause the device to malfunction, or use the update system to install old versions of the software that have known vulnerabilities. In Beaver Summer Institute's Embedded Security and Hardware Hacking course, students are put through an exercise of designing and implementing a secure software update system and then learning from their mistakes. After completing their systems, each team does a security evaluation on each other team's system in an attempt to identify and exploit both traditional cyber vulnerabilities as well as vulnerabilities that require physical or proximal access to the device. I hope you are looking forward to the student presentations as much as I am. All right, well, welcome everyone. Today we have 7 presentations, one from each team that competed in our design challenge this summer. So if the first team, Non-Zero Exit, wants to share their screen and get started with your presentation, we can kick this off.
Okay, so hello everybody. This is a presentation for Team Non-Zero Exit. And so our team name was definitely inspired by one of the errors that we faced a lot early on in the 4 weeks, but we did a lot of problem solving, but also ran into a lot of issues throughout the program. So we thought it was a pretty fitting name. And so my name is Madeline, but our other teammates are Alice, Luke, and Clarice. And these are just the postcards that we made. We won't go too much into that right now.
So this is an overview of our protocol and a flow diagram. The FW Protect, BL Build, FW Update, and Bootloader were the 4 tools that we used to implement our system. So initially, the BL Build will generate the IV and the 16-byte key, which is used for AES encryption in GCM mode. Then the BL Build tool will generate the 32-byte key, which is used to generate the HMAC. Then the HMAC and the tag, which was generated in AES encryption, which is basically a second check of authenticity. The metadata and then the firmware will be sent to the FW update tool. The update tool will then construct this data into frames. Our team chose to choose a frame size of 18 bytes, with 2 bytes being the length of the data and 16 bytes being the actual data itself. Then the bootloader will read in the HMAC and the tag. Then it'll read in the encrypted firmware and then calculate and check the HMAC. If the HMAC matches, it'll decrypt the metadata, which gives information on the firmware size and firmware version. And if it is a newer version, it'll decrypt the rest of the firmware data. Then it'll check the tags, and if the tags match, it'll install the frames. So therefore, if the calculated HMAC doesn't match, or if the firmware version is an older one, or if the tags don't match, it'll terminate installation.
So we had to consider the different ways attackers could attack us. So one type of attack we protected against was a version rollback. So which basically meant attackers could send older firmware into our system. And so we protected against this by using the metadata to determine the version of the firmware and just like make sure we had the correct version coming in. Another type of attack was a differential tower analysis. And in this type of attack, the attacker would be able to feed in a lot of data and just figure out what our HMAC key was just by analyzing the power traces. And so we protected against this by verifying the HMAC before decryption. But this attack was mostly like theoretical in nature because we didn't have access to actual power tracing tools.
Yeah, so just a little bit more about the attacks we considered launching in other teams. So there was first the rollback flag, which was the first one that we thought we wanted to focus on. And so just an example of some things that we're thinking about. So for one team, we noticed that they encrypted the metadata and firmware separately. And so we thought that we could exploit this and that we could intercept the firmware and copy it so that we could actually send it with new metadata later because the metadata and the firmware weren't necessarily correlated. But then we realized that this wouldn't work because the team was using a key stream. And so if we kind of switch things up, then the keys would not actually match. So that was a little bit disappointing, but that was one of the early on ideas we had. And then like Alice said, because we had to protect our own program from a DPA attack, that was another way in which we thought we could attack other teams, but we didn't have the resources or the time to do that necessarily. But we definitely thought that if we could run the program enough times, we could collect enough data to potentially pull the keys from. So that was more of a theoretical attack that we were thinking about.
So I guess at the end of the day, many teams share very similar designs. That means that we can identify the vulnerabilities in our code, and we're going to use it to exploit the same problems in the other teams' designs. So what we do first is we are going to focus on teams that have a flow diagram, because I guess flow diagrams help us recognize the kind of system they set up, and this is going to help us sketch out some ideas for attacks. And we're going to import them into our own lab, and we're going to try to do some experiments on these designs. So there are still many problems with our system. First of all, buffer overflows and vulnerability in our codes, because C by itself doesn't do a lot of bound checks, especially with the functions we used. So buffer overflow is a problem. And the second problem is that we have too much memory usage. So we have two 30 kilobyte buffers, which is using up 60 kilobytes of memory in total. And this is actually a huge problem on microcontrollers. And this can lead to unexpected problems down the line. The code works so far, but in the future, it might not.
So fortunately, our team was able to capture a flag 15 minutes before the attack phase had ended. We captured the invalid firmware flag, and we were able to do this because we saw that one of the teams had a vulnerability because they had an HMAC for each individual chunk of data that they were sending to the bootloader, but they had no check for the correlation between each chunk of data. So we wrote a Python script that deleted basically a chunk of their code, and they had no integrity check in the bootloader, so we were able to capture their flag.
Yeah, so after we kind of focused on the rollback flag initially, then we kind of switched our focus to the invalid firmware flag, and so we did a lot of work on that. Okay, and yeah, this is just kind of a fun slide. So throughout the program, we learned a lot, but it was definitely exhausting at some times, but definitely lots of fun and very worth it. And so to kind of take brain breaks every so often, we like to do a lot of drawing, whether it was just drawing hearts all over our programs or drawing our amazing TA, Arthur. Thank you, Arthur, for all your help. Or doing hangman games that had encryption themed words. We had a lot of fun, but also learned a ton. So thank you.
Thank you.
Thank you.
Thank you, Non-Zero Exit. That was great. And I look forward to using that picture of you getting that flag and being super excited. That's awesome. So if there are any questions for Non-Zero Exit, you can post them either in the Zoom chat or submit them via Slido. Or for other students, you're welcome to just voice your questions over Zoom. I have a question. So over kind of the whole design and attack phase, what do you think was the most difficult thing? What was the biggest challenge that you felt like you had to overcome? I know there are a bunch of challenges throughout the whole course, but what's one that really sticks out?
I think for me personally, I definitely struggled with C a lot throughout the program, more so than the Python programming part. So I guess because in order to attack other teams, you really had to have a solid understanding of what exactly the other team was doing in their bootloader code. So definitely kind of analyzing the bootloader code, working through that. That was probably the most difficult part, just kind of figuring out, like, if this was our program, what would we do differently? So that part of the analysis.
Awesome, great. Yeah, we'll try to add in more C programming for the next year's students. Thank you. All right. Well, great job. We'll give some snaps for Team Non-Zero Exit. And next up, we have Team 3.
Hello. So we are Team 3 of the Embedded Security team. Our team name is Team 3 because we are Team 3. Talking about our teammates, my name is Nick. We have Albert, Chen, and Sherman.
Just a general overview of our protocol. We used a combination of GCM as well as a Caesar cipher, or two Caesar ciphers. So first we encrypt the firmware, the release message, and the null terminator using a Caesar cipher. And then the result of that gets split into 1 kilobyte pages, each one encrypted using a 32-byte key using ASGCM. And we have the metadata as additional data for authentication. each round requires a unique 16-byte IV, and it produces a 16-byte tag for authentication later in the decryption. And after the GCM finishes, we have a round of Caesar that will encrypt each page again. So we have the encrypted pages, but the metadata, the IVs, and the tags are all unencrypted. The decryption is just the reverse of the process, except we read the metadata in first, and then we decrypt the first page until we decrypt the metadata, or the authentication tag of the metadata, because we don't want to be writing anything to flash that we're not supposed to. And then once, or if the metadata is successfully authenticated, we will decrypt using Caesar, GCM, and then Caesar. And then if everything is successful, we will install the pages. So here's a just general flow diagram of our encryption and decryption. So if you see on the encryption, something to point out is that our Caesar server, there's a 1-byte key input, which just denotes how much we shift each byte by. And these two keys are different from each other. And in the decryption, you can see that we are authenticating the metadata. And if that doesn't work, we terminate the installation. And then we can continue the decryption after the successful authentication.
So through the implementation of the AES GCM and the Caesar primitives, our design was pretty well protected against brute force attacks. That's because we had a 32-byte key, a 16-byte IV, and a 16-byte tag, which is obviously difficult to brute force. Another pretty strong threat to our design is the buffer overflow attack, because our bootloader code is written in C. And C does not provide any default protections against like overriding and accessing data in memory. Therefore, we refrain from using methods such as string copy and printf, which will happily write past the bounds of the buffer. Towards the end of our design phase, we saw that if with only the GCM primitive, if the attacker was able to crack this primitive, then the Caesar cipher would corrupt the valid firmware, and the attacker would not have to input malicious firmware. To fix this problem, we implemented the other slice of the sandwich, or the second Caesar cipher, which gave our design a little more integrity and confidentiality.
While we were able to protect against some attacks, we weren't able to protect the project from every attack, especially the one that involved the pages being sent in a different order. While we used the implementation of the tags to authenticate each page itself, we weren't able to encrypt the page value, so we allowed, other teams to change the orders and attack our project. Also, the main threat that we considered in our process was the side channel attacks. However, with this year's design challenge being operated without any tools to stimulate power traces and other side channel attacks, our team was able to consider more algorithmic attacks as a threat instead of the hardware.
So our primary primitive was GCM, Galau counter mode. And this primitive is symmetric key, meaning that in both the encryption and decryption processes, the same key is used. So in this primitive, this primitive is a block cipher, and it uses an IV, an initialization vector, and plain text to generate both ciphertext and an authentication tag. We implemented GCM in our firmware protect tool for encryption, and we decrypted in the bootloader. This primitive ensured confidentiality, integrity, and authentication. And as you can see below, those were our inputs and our outputs in the encryption. So here's a diagram of GCM. So basically what's happening is the initializations vector is passed in as a counter, and it's incremented 2 times as counter 1 and counter 2. Then the counter 1 and counter 2 encrypted and XORed with plain text to yield a ciphertext. After, it's just a series of XOR operations and hash functions. Those hash functions are the mul h. And towards the bottom right of the diagram, the len a represents the length of the authentication data, which was our metadata, and length C represents the length of the ciphertext. And after this entire process, an authentication tag is produced.
Aside from the usage of GCM, another cryptographic primitive that our team implemented was Caesar Cipher. To describe the basic implementation process, we first generated two 1-byte keys from our BL build tools, in which was used as a perimeter of shifting for our Caesar Cipher encryption. Mentioning a special slide over Caesar Cipher, with the Caesar Cipher key generated in BL build being generated as a byte, we convert it into an integer, incrementing and shifting the plain text before and after GCM, adding a pinch of confidentiality to our project. Talking about some of our future plans. Considering that we weren't able to do side channel attacks, in the future, we plan to implement some encryptions for hardware or other side channel attacks that could potentially harm our project. And going back to our vulnerability, we plan to encrypt and send page number to try and prevent flipping orders. Going off the basic future plans, we plan to learn and adapt ourselves to more attacks and other implementation so we can further our knowledge of other attacks and prevent them from attacking our codes.
So for the attack phase, unfortunately, our team wasn't able to get a flag, but we did identify several vulnerabilities in the other team's code. To start, we searched for two main vulnerabilities. One, loops that did not have explicit stops. Essentially, what this means is that if there is a loop that is based on a length that we can pass in, we can alter the amount of data that is being read in. And since in C, everything has a pointer to a memory address, if we can keep reading in information past a certain set of size set for a certain variable, for example, a data array, we can write past that value and go into other addresses. And essentially for this attack, we want to search for a firmware size or a firmware that's big enough to overwrite into stack pointers, thus allowing us, giving us control over where the program goes. For the second vulnerability, we were looking at unprotected flashing. Some teams did not protect their metadata flashing, which allowed us to change parts of the metadata. So for two teams, for one team, we discovered that their data...
Hey guys, I'm sorry, I'm gonna have to cut you off here because we're a little bit over time. So I'm sorry to stop you here. I'll maybe give time for one question. And for all those watching, you're welcome to go watch their recorded video, which includes their whole talk. So I guess now, before we transition, are there any questions for Team 3?
I have one question I can ask. So in terms of identifying security vulnerabilities in your own design, were there any vulnerabilities that you knew about before you submitted your code versus like learning about after, or are all the vulnerabilities that you kind of learned about your code, did you discover them after submitting your design?
So basically there were two vulnerabilities in our code that I identified, right? Technically three. The first one was the Caesar one. So if they were to get over GCM, our own valid firmware would be corrupted by our own code. That's for before we submitted our code. But for the other two, we discovered it after learning about the attacks being done. So the first one was that our buffer for the data, we read in frames. But the thing is, we didn't like account for a certain set frame. So they could have set the frame to a really large number and had data being overwritten to other variables and addresses. As for the second one, this was pretty common in our attacks. The pages, people managed to shift around the pages. And since we only encrypt and decrypt per page, there was valid decryption and verification, but it still became invalid firmware because the parts of the firmware got shifted around.
Great, thank you Team 3, snaps for Team 3. And Next up, we have the B team.
Hi, everybody. We're the B team. My name is Meghna.
I'm Ritika.
Yeah.
And I'm Anisha.
So, the goal of our project is to design a secure system for a hypothetical self-driving car. We have to make sure we can send updates to it whenever we need to, but other members of our class may send malicious firmware updates, and we must protect against those.
So this is the general flow of our firmware protection process. First, the actual firmware is encrypted to preserve confidentiality. Without the secret key to decrypt, it's very hard to understand. A public initialization vector, or IV, which is also used for encryption and decryption, is appended to the end of that. So after, a large data blob is made, consisting of the version number, firmware length, encrypted firmware, and release message. The size and version number is called the metadata because it's data about the data. Taking this metadata, a hashed message authentication code is created, or an HMAC. An HMAC preserves the authenticity and integrity of the firmware because it uses a secret key to make a unique tag out of the firmware. If the actual firmware is changed at all, this tag won't match up. So then the big data blob is split into 32-byte chunks, and the HMACs are generated for each of those chunks as well. We then have 3 final HMACs, one for the first half of the data, one for the second half, and one of those HMACs.
The update tool's job is to split up the encrypted firmware from the protect tool into frames and send them to the bootloader to be decrypted. The update tool is located in an insecure environment. This means that it can be exploited by hackers in their basements. Our update tool works by breaking up the encrypted file sent from the protect tool into metadata and its HMAC, frames with the HMAC attached, and the final 3 HMACs. The bootloader uses these HMACs to verify each frame and to check the integrity and authentication of the frames. If there are no errors, the bootloader will decrypt the ciphertext and write it to flash. When the update tool receives the message to update, the bootloader will boot with the new firmware.
We learned about many malicious attacks in these past few weeks, and we wanted to protect against as many of them as we could. We mostly focused on the man-in-the-middle attacks because we expected other teams to employ this the most often by switching around or dropping frames to boot invalid firmware. And as we discussed, we preserved order with the HMACs. Additionally, even though we didn't expect many side channel attacks like DPA and SPA, we made sure that functions that could give away secrets used the same operations and had constant time regardless of the case. This came with some minimal time increases, though. We were also conscious of the buffer overflow attack and made sure we sent constant sized frames and limited the size of parts of the firmware and release message. However, this technically wasn't successful, which we'll talk about later.
So one of our important security feature highlights was the heavy HMAC usage. Even when we did not encrypt the data, we still added an HMAC to authenticate the data. Another security feature was the isSame function, which goes through the given and calculated HMAC and returns whether they are equal after going through the entire HMAC. This prevents against SPA attacks.
Obviously, given only a couple days of development, our protocol wasn't state-of-the-art secure. So if we had to go back and improve our design, we probably would add an extra layer of security by using AES counter mode, which is an extra secret key to preserve, confidentiality. We would also change our design to be less susceptible to buffer overflow attacks by having more fixed size variables and fixed length arrays. Buffer overflow is when an input is given that is larger than the allocated space, so the input overwrites surrounding code and values. Having fewer dynamic variables would allow for less flexibility, so malicious input would not cause buffer overflow attacks.
For the attack phase, we looked at our design and focused on what we were protecting, like the release message, the order of frames, and side channel attacks. We decided to focus on the release message and the order of the frames. We tried different ways to use buffer overflow on the release message, but we had a hard time controlling the overflow. When we made our design, we were careful to make sure the frame order could not get messed up using HMACs. But when we looked at other teams, we found that some did not protect against this, and this is where we focused our attack.
After looking at a team's code for a while, we saw that the way they organized their bootloader left it vulnerable to the invalid firmware attack. Even though they checked for authenticity and integrity, they did so for individual frames, which meant that we could recognize the way that frames were sent over, reorganize the way that frames were sent over without our malicious actions being detected. We came across some challenges when booting the messed up provision firmware because initially we removed frames from the beginning of the firmware, which might have damaged some critical information. Instead, when we removed frames in the middle of the firmware, we were able to boot the malicious firmware and successfully obtain the invalid firmware flag.
In summary, we designed a secure system to update car firmware, and we attacked other teams' code by removing a frame and booting the firmware.
None of us worked remotely, so it was really good to improve on this. And then we also increased our collaboration skills, and we learned to work together with GitHub and stuff like that.
We would like to thank our instructors for taking their time to teach us during this course. They were very patient with us and would always help us understand what we were doing when we were confused. We'd also like to thank our sponsors for giving us this opportunity, and we'd like to thank Beaverworks for this wonderful experience.
We've learned so much from this course, ranging from embedded systems to cybersecurity to teamwork over Zoom. Lastly, we would like to thank the programmers who wrote the code that we used for successfully rickrolling us 5 times. Thank you so much for listening. Are there any questions?
Thank you, B team. That was great. I was worried that there weren't going to be any B puns in your presentation. So I'm happy to see this on the last slide. All right. Are there any questions from someone in the room? Or I'm now paying attention to Slido as well. So if there, all right. So we got one question on Slido, which is, what was the system these protocols were implemented on? How easy would it be to port this protocol to other systems?
Well, I think that every system is a little different, so you can't just transfer exactly. But the way our system works, it's really just like importing the right libraries, and we were using an emulated Stellaris. So if it's similar to that, it probably would be easy for you to transfer the code.
Alrighty, thank you so much. Snaps for the B team. Next up, we have the goats. And for the question and answer period, please unshare your slides so that we can have the gallery view for the webcast.
Hey everyone, so we're the goats. I'm Ingrid and my teammates were Seth, Andrew, and Bronwyn. So an overview of our protocol, in our BL build tool, we provisioned 2 random keys. So that was a 32-byte password to the HKDF function and then a 16-byte metadata HMAC encryption key. And then to protect our firmware, we generated 2 more keys from the HKDF function. So one for HMACing the firmware and one for AES encryption. And then after that, we would HMAC the metadata with the 1 provision from BL build. And then we would use AES 128 and HMAC with SHA-256 for each 16-byte firmware blob. In firmware update, we would send through each 16-byte firmware blob, and we sent our data in 50-byte packets, 2 bytes for length, 16 bytes for the firmware, and 32 bytes for the HMAC. And then finally, in the bootloader, we would verify the metadata using the first provision key, verify the ciphertext, and then decrypt everything and boot it up.
So in order to generate our cryptographic primitives, we decided to use HKDF. That way we can generate an unlimited number of keys as we needed without having to store all of it on a list in the bootloader, which may have taken up more space than the Stellaris could have handled. So we pass an assault and a password, and we use it to generate our AES encryption and HMAC keys. So for our confidentiality, in order to protect our data, we decided to use a tried and trusted AES 128. It can't be cracked, or as of yet, and it was more than enough for our purposes. To ensure that the firmware that we're getting is authenticated and not been tampered with by hackers, we've decided to use HMAC. What that does is create a hash of the message we sent along with the message itself, and that way the bootloader can create its own HMAC by checking the data sent in order to make sure that it matches the HMAC sent. So to the right, you can see an overview of our protocol. We first encrypt our data before hashing it. What this means is that when you want to decrypt or get the firmware plaintext, you would have to verify the HMAC first before decrypting, meaning that attackers can't spam our protocol with a bunch of dummy firmwares in order to extract information about our key.
The security highlight of our protocol is definitely HKDF, and HKDF is a pseudo random key generator. This allows us to have a master password along with a salt, which manipulates our key generation. And this allows us to have rotating keys for each and every firmware and each and every update that we would want. And so this prevents people from doing side channel attacks where they could analyze our power usage to get a key. because we can just swap out keys whenever we want to. Some attacks we considered when building the protocol was poisoning our metadata. So we made sure to add HMAC for authenticity for our metadata, so people couldn't edit our metadata and therefore affect how our protocol worked. We also worried about key attacks, specifically side channel attacks, where they could read off radio waves or power consumption off our bootloader. And so we prevented that with our HKDF key generation. And we wanted to prevent version rollback. So we made sure to flash a permanent resident for our version number, so we can always refer back to that to prevent a earlier version to be loaded onto our bootloader. Some approaches to our attack phase was looking at other teams' code and seeing if we could do a buffer overflow attack. And a buffer overflow attack basically means we would overload a certain variable in our code, which could allow us to overwrite other variables or even jump code. We also were looking at rollback version vulnerabilities to see if anybody was flashing prematurely to the metadata. And then we were checking vulnerabilities and unchecked firmware and metadata, such as while loops that would continually receive firmware, which would open up buffer overflow attacks for us.
So in conclusion, if we were to do this again, we would, I guess, maybe not use HKDF because the time that we ended up spending on it was not advantageous compared to the benefits of using HKDF. And then we also had some implementation issues, and what happened was our code ended up being very convoluted that it was very hard to debug. So yeah, any questions?
Thank you, Team the Goats. I appreciate that reflection at the end. All right, so do we have any questions for the Goats from online or from any of the panelists? Let's see, so I got a question. So you mentioned that your code got a little convoluted at the end and it made it difficult to debug. What steps would you take to remedy that problem if you went back and did this challenge again?
Well, I guess what we would do is follow more like a coding format structure, like a standardized version. And we would probably add more functions to what we would call, because right now we have all of our steps in one function, and it would be useful to split it up and just call functions. And that makes it easy for us to pinpoint where our problems are in our code.
Awesome. Thank you. All right, snaps for the Goats. And up next, we have error 404, brain not found.
All right, we're error 404, brain not found. I'm Cora.
I'm Mekai.
I'm Ben.
I'm Gary.
This is our design diagram, which shows the distribution and flow of firmware and different Python tools containing our code to do so. So the first tool that we used was the bootloader build tool, which is in the secure environment, as you can see. This was to generate an infinite string that would later be used to generate keys for our encryption. This string is known as a key stream and was generated based on the RC4 stream cipher. So a quick overview, the string was first made by generating a random 16-byte long key, which is stored in the secret build output.txt file. And then the firmware protect tool, which will be mentioned later, used a KSA or key scheduling algorithm and a PRGA or pseudo random generation algorithm to swap values in the key and generate the final key stream. And this bootloader build tool also generates a main.bin file, which contains the contents of flash memory.
The next Python tool that we used was the firmware protect tool. This creates metadata for our firmware and firmware, including the firmware version and the firmware size. It will also eventually include HMACs. But the protect tool first creates an HMAC of the firmware, and then again one on the firmware of the metadata on the version and size. And these are using two different keys through the stream cipher that Mekai was talking about. It then breaks down the firmware into frames, with the first 16 bytes being an IV, the next 2 being size, and then a 1 kilobyte frame of ciphertext that is encrypted through AES. And then the tag, authentication tag, is the last 16. This tool then packages that all up and sends it over to the update tool, which is in communication with the bootloader to upload all encrypted files and any metadata in chunks through a specific protocol. In our case, it sent over the metadata first and then sent over all necessary data in select frames.
So the cryptographic primitives that we use, we primarily use an HMAC for authentication. So an HMAC provides a hash, which is essentially a one-way function that provides a unique result that is authenticated through a shared key. We use 2 HMACs, one on the firmware and one on the metadata. The next cryptographic primitive that we used was a stream cipher that was just used to generate different keys for hash functions and AES encryption, as aforementioned. This stream is generated based on a secret seed key, and the specific key is generated through additional secret numbers. And the primary cryptographic primitive that we used in order to preserve the integrity of our firmware was AES in the GCM mode.
This is just an overall flow diagram of how we encrypted and protected all of our data and how it was updated.
So, who are we actually defending against? Well, this is our threat model. We're defending against our classmates, right? Our classmates have been able to learn the exact same material as we have. They have comparable skills, and they're able to use all the attacks that we know how to use. So, if anyone tries a man-in-the-middle attack, where one might change the order of the frames in the update tool, we decided to put in HMAC on the original state of the firmware so the bootloader can check the order of the frames after decrypting everything. Also, general confidentiality attacks were protected through the GCM AES encryption.
Our security highlights are ACS GCM. This encryption provides both, or not both, all 3 specific things of confidentiality, authentication, and integrity. It encrypts the data within AES encryption, but also produces an authentication tag with the same key. So the bootloader will be able to authenticate the firmware and know that it's coming from the right place. And our firmware and metadata hashes were also important, as it provides integrity to the firmware and the metadata, and it prevents any other teams from trying to swap any of our data.
If we were to do this challenge in another way in the future, we would make use of some sort of asymmetric encryption like RSA. Asymmetric keys would be useful in case of any key leakage in the build tool or any other Python tools mentioned earlier, but a downside to this would be that it would use a lot more memory than we currently are using, and that could lead to more difficulties. A more secure version checker would also be another improvement we can make, because right now our version checker is only a few lines, so a potential fault attack could be implemented against our current version checker. But in this design diagram, we didn't have to protect against these fault attacks because it wasn't a possibility in our course, but it's a vulnerability that we could fix later on. And another possible attack against us, which has been proven possible, is that an attacker can upload a large invalid firmware file, which clears half of the current firmware and then boots the remaining now invalid firmware. And in order to protect against this, we would need to implement a better system for clearing and storing memory in Flash. And we saw this vulnerability after submitting our design.
But moving on to attacking other people's bootloaders. One big part of cryptology is protecting the integrity of the data that you're trying to decrypt. This means that someone can take encrypted data, move it around, and then submit it as their own. That's not good, because it can potentially cause malfunctions that won't be detected by a key since it was encrypted with the same key. It was just rearranged. And we noticed that some teams did not protect against the attack through the use of such as an HMAC or something, which would have helped ensure the integrity of the files. So if you see here, I wrote a quick Python script that opened up a team's firmware blob, recorded down different parts of the data, and then rearranged it and wrote it back to the firmware. Now when we try and update this firmware to the bootloader, it'll still get accepted because it's using the same encryption algorithm and decryption algorithm. It's just that the data was switched around. So when you try booting the firmware, you'll get a corrupted version, essentially crashing the system.
That's all. Thank you.
Awesome. Thank you, Error 404, Brain Not Found. Do we have any questions for the team? All right. Well, I got a question. So similar to the first question I asked, or the question I asked the first team, which was of all the weeks or in all aspects of the design challenge, what was the kind of #1 challenge that you faced or struggled with?
Well, I would have to say it's the attack phase, because when we were designing our own bootloader, it was sort of straightforward, putting our ideas onto the code, especially because thankfully people already wrote these sort of code that we can import and use it, such as bare SSL, and all we had to do was get through a little bit of documentation to implement it. But trying to exploit other people's code was much harder because it sort of was more like solving a puzzle. It was more free. You didn't really have a set of instructions to follow. And I found myself for a couple hours just staring at people's code, trying to see what was wrong with it, and I couldn't find anything. So I would say that attacking was probably the most difficult.
Alrighty. Well, snaps for error 404, Brain Not Found. And up next we have Completely Insecure Alice.
Ryan, Kelly, Suzanne, you guys there?
Hello, everyone. We are Completely Insecure Alice, which stands for the CIA. And I'm Ryan. There's Charlotte, Suzanne, and Kelly.
Yeah. And here's a nice picture of us, so you know what we look like.
All right, so for an overview, I won't go into too much detail because it's almost the exact same as everyone else. We write keys to the bootloader. We use an AES and an RSA public key. And then when we protect the firmware packages, we sign them with AES and RSA. And RSA is our one main differentiating factor, so I will go into RSA a bit later. For the actual firmware update process, it's also pretty similar. What we do is we split the update file into chunks of up to 1,120 bytes, and each chunk contains all the signatures, the encrypted payloads, some metadata, and the bootloader will reading the metadata, verify that, and then reading the frames for the entire chunk. And once it gets the chunk, it will verify all the contents of that chunk and make sure it matches with the signature. And once all of that is good, then it will copy it into the firmware. One thing that we really focused on was documenting all of our code, because documentation points are also awarded in this design challenge, and the max documentation score is 1,600 points, whereas being the first to get a flag will only give you about 600 points. So we really went after the documentation. It ended up being 10 pages, which, yeah, it's what it is. Okay, so for the actual packets that we sent, what we did was we encrypted the firmware itself with AES, because AES is fast and designed for this kind of thing. And then we used RSA to sign both the metadata and the firmware together, because RSA uses an asymmetric key structure, which helps protect against an event in which our keys from the bootloader gets leaked. There's a nonce in each packet which differs between them, so that the AES has that additional layer of security.
So here are some of the highlights of our design. The invalid firmware attack was definitely one attack that we considered, and we tried a few different methods to protect against against this. So we independently encrypted and signed each packet, and each packet had their own index. So this ensures that they are sent in the right order and attackers won't switch the chunks around. And as for the RSA signature, both the metadata and the firmware binary were signed together. So this provides more layers of security, and this was actually one of the vulnerabilities that we found in some of the other teams' codes. So this was interesting to see. And on the bootloader side, we firmware size by writing the frames to a type address, and then once everything is received, we check that the number of bytes match the firmware size, and then we are able to write to the actual address.
So some of the potential problems with our code is that we didn't check for buffer overflow at all in our code, since that was an attack that we studied before we wrote the code. As a result, block ciphers are still prone to memory issues, and we assumed that the signing would make the length trusted, so we actually didn't do any bounds checking, so that could be a vulnerability. And last of all, the system doesn't really handle bad input, it will just reset the entire system. So as fixes to these problems, we would have rewritten the code and the variable assignment to test for buffer overflow vulnerabilities, length checked all of our inputs, and also probably establish a better communication protocol for errors, say resending a frame or so.
So, as Charlotte said, because we didn't actually do any bounds checking, and we just kind of, like, our code would only validate the firmware once it said it received everything, and so if you just sent a bunch of data to it, it will just take it in, which is kind of a big vulnerability. But despite that, no one actually attacked our team. We think, like, us, our team, and another team were the only two teams that implemented RSA and signed everything. And we also managed to add colors and animations to, like, our update tools, which some people have commented on as, at least that was scary, I don't know. Outside of that, our code was relatively similar to everyone else's.
Now we'll talk about the attack phase, where we try and attack other teams' design. And in order to achieve that, we first look at their source code and try to understand their protocol to try and uncover vulnerabilities. And one of the attacks that we went for was the invalid firmware attack. And well, when we're investigating other designs, we found that most teams were HMACking each of their firmware chunks separately, and therefore there was no security to the order at which the chunks are sent. So if we somehow managed to swap two or more of those chunks, we could successfully corrupt the firmware, but the bootloader will still accept the firmware because the HMAC was still verified.
So the first attack we did is actually on the B team. The issue with their protocol was that the metadata and its HMAC was created separately from the rest of the firmware. So therefore, we could change the metadata and HMACs of different versions. So thinking of this vulnerability, we originally attacked it both the rollback flag and the invalid flag. We thought that if we put a higher version's metadata onto a lower version, we could get it to run. However, since different versions have different sizes, which was also in the metadata, this attack didn't actually work. However, the invalid firmware did work, because since it's a different size, it didn't read in all of the firmware, and when you cut out like a fifth of your code, the code obviously does not work.
The team did, like the B team HMAC'd every single frame, and then they HMAC'd all the HMACs together, so the firmware was really secure. We could not break into that.
And the second attack we did was on the goats. This was exactly what Zah talked about. Each frame of the data was protected separately with HMAC, meaning that the order of the data is not protected. So for the attack, we just took the firmware version 0, went to the middle of it, found a random 51-byte chunk, took that, and then copied it somewhere later in the firmware, and we updated with the corrupted firmware. And it didn't boot very well.
All right, so error 404 Brona found, when we were looking through their code, we noticed that they had an interesting design choice where they actually wrote the firmware, like the firmware that they received, to the flash before checking it. And then after they write it, they would then validate the signature. And if the signature was invalid, they would try to undo that. So the issue was that when you call flash erase, it will always erase a 1 kilobyte chunk of flash. But we didn't have to send. We were able to simply say, oh, here's 10 bytes of bad data, and then the loader would freak out, and it would delete an entire kilobyte of flash, and therefore corrupting the firmware.
And that's all. Thanks for coming to our presentation. Any questions?
Thanks, Completely Insecure Alice. All right, do we have any questions from the crowd? And I'll keep my eye on Slido.
I have a question. So you said that you switched from using a zero-length frame to end the firmware update and just switched it with like some sort of other signal. Why did you choose to make that change to the protocol?
Well, I think the main idea behind it was that we wanted to send everything in basically the same format. So we would send the chunk metadata, the chunk info. So we wanted to keep that format. And we didn't, so instead we changed something in the metadata to tell them that this is the last package that would be sent.
Cool, thanks.
Yeah.
All right. Oh, go ahead, Ted.
Oh, my camera's not working. But so you said you use RSA to provide authenticity. I'm curious why you chose to use RSA, and did you come across any difficulties while implementing it?
Well, we chose RSA due to its asymmetric nature, because we knew that there's been plenty of attacks when keys have been retrieved from the bootloader, especially in like high profile, like with Nintendo, for example. That used to be a big issue since everything used one key. So that's why we chose RSA. As for implementing it, because RSA was not one of the libraries we were provided with, it was quite difficult for us to try to figure it out on our own. But we think it was worth it because.
All right, snaps for Completely Insecure Alice. Thank you. And up next, and our last presentation is from the Shifters.
All right, so we are Team Shifters from the Embedded Security class, consisting of me, Aiden, Zawad, Alex, and Tom. And the reason we named our team the Shifters is because we were originally intending to include a Caesar cipher somewhere in our project, but it ended up not being implemented. First, here is our flow diagram. I'll go over our protocol in this black box on the left, and you guys can follow along if you want on the flow diagram on the right. So what we did was we had a block of data called metadata, which would just store the version number, the size of unencrypted firmware, and the size of encrypted firmware. And then we would hash that using the secure hashing algorithm 256 or SHA-256. And then we would proceed to sign that using the RSA asymmetric method. Then we would append that just to the plain text metadata so that we could obtain that on the other side, on the bootloader side. Then the IV or initialization vector for AES encryption, which would then allow the encrypted firmware to be decrypted on the other side of the factory.
So when we were designing our model, we were thinking of, okay, what are some possible threats we could face when we eventually get attacked? So first up, we already decided on using RSA and AES, and those algorithms are, of course, limited by the computational power we have, but most people who are probably going to attack us don't have like quantum computers or like very powerful computers that can brute force our algorithms. So we figured, okay, we can implement this correctly. We should probably be safe on that front. While designing, we consider replay attacks, buffer overflow attacks, and side channel analysis attacks. But this year we're virtual, so we thought, okay, we're probably most likely safe from the hardware attacks from like side channel analysis and EMFI. But while designing, we specifically did write protections against buffer overflow attacks and replay attacks.
Cool. So the one interesting part here is that we were one of the first teams to implement RSA in supposedly the history of this class, as far as we know. And it turned out to be a very secure way of encrypting and verifying our firmware, and it really helped us out.
To prevent against the buffer overflow attacks, which would then write into stack and allow them to execute whatever code they wanted, we would set a hard limit on the data size accepted at 31 kilobytes, which was the maximum amount of data we would actually have to accept. And we checked the encrypted size multiple times, and we only accepted that many bytes. So basically, they could not write any more than they said they were going to write. And if they said they were going to write more, we immediately rejected it. So this would be pretty good protections against overflowing the buffer and overwriting any other place in memory, aside from the very specific chunk of memory that we have allocated.
Despite all of these design protocols that we came up with, there are a few things that we would change next time. The first thing is trying to become familiar with C topics a little bit earlier. This would have helped the whole team be able to debug our code more effectively and more quickly. Next would be getting more familiar with the API that we used, which mainly was BWSI, which is an encryption library made specifically for embedded systems, and it's made to be very efficient, but it also has not very optimal documentation, making it slightly difficult to implement. Then finally, if we were to not be virtual next time we did this, we would implement measures to prevent hardware level attacks, such as side channel attacks. The reason we didn't have to prevent against those types of things this year is because the hardware that we were sending our firmware to, the Stellaris, was emulated, so power and voltage and current readings could not be taken from it.
So when we approached the attack phase, we first off had to analyze other teams' code. So we looked at their how they approached their security and how the algorithm they used. So we specifically looked for things that we know we designed against and oversights we almost had ourselves, and we thought maybe other teams wasn't able to find that. And we were able to use the GNU debugger tool, which is GDB. So we were able to analyze more closely of how these programs work on the assembly side of it, and we were able to perform binary exploitation and find memory addresses through close analysis of other people's programs.
The team that we attacked was a non-zero exit, and we realized that they returned from the function following an HMAC verification failure without resetting the chip or wiping anything from memory. And they also had an unbounded buffer that allowed us to write whatever we wanted past what was actually allocated. So we sent in a carefully crafted chunk of data that overwrote the link register and pointed back to itself, such that when the HMAC verification failed and the function returned, it jumped, instead of back to main function, it jumped to our firmware, meaning we have just gained total control of their device. This allowed us to steal all their keys and read all their memory and write it to whatever files, which then allowed us to decrypt and re-encrypt invalid firmware from like version 1 and authenticate it as version 4 while acting like the factory. Something like this is why we used RSA to prevent against stealing keys, because even if they stole keys, they couldn't authenticate the software since the private key was still hidden.
Right, so I think we have some time for Q&A, correct?
Yeah, thank you, Shifters. Any questions from the crowd or from the audience?
I was actually wondering how you guys managed to get the keys from like running your firmware. Did you guys like have some like instructions that you translated to binary?
Yeah, we wrote into the firmware that we sent. We told it to dump memory starting from hex 20 million onwards, and we wrote it to an empty binary file that we then used XXD to analyze as a hex dump, and we saw something that looked like keys, like the HMAC keys, the IV, and the AES key. So we were able to take those keys out of the hex dump and attempt to decrypt it and verify it on the GCM encrypted firmware version 1. Once we decrypted that, we were able to get the intellectual property flag and re-encrypt it as version 4 to get the rollback flag.
I see. Thank you.
So it was really just a bunch of guessing to get the keys.
All right. Any other questions?
Sorry.
Go ahead.
One thing I want to mention is if someone else is trying to do a similar attack, if they ever have the chance, if you get a lot of weird results like corrupted looking stuff, basically if you get a lot of question marks and boxes, that usually means that something is being cast to a string. So basically try to not view the data as a plain text. Try to first take it and put it into a binary file and then analyze it with a tool like XXD or something similar.
Yeah, we wrote it into a binary file with we had the pathological update tool that would upload the firmware, and we had it communicate with the firmware we sent over UART1.
Yeah.
Right. All right. Yeah, my last question is, had you ever done a buffer overflow before?
I actually didn't think I could do it. Then we just did it. I only ever heard about it in ways to credits warp in Mario.
That's great. All right. Well, thank you so much, the shifters. We are all done with the presentations, and we have 9 minutes left before the next session. So I want to open it up to the panelists and the audience to ask questions to any team. I have a few questions that we didn't get to ask to Team 3, so I can start with those. So Team 3, the first question is, when and how was the initialization vector generated in the first GCM model, and how often did you change it?
Can I show my screen, like the actual code?
Yep, go ahead.
Let me show my screen. So for that question, how often was it generated? We generated a random 16-byte IV or initialization vector for each page, and each page was 1,024 bytes. Here you can see that we're generating an IV here, and we're looping till the end of the firmware for each 1,024 bytes, if that answers the question.
Great, thank you. And then one more question for Team 3. From what you've learned during the competition, how has that new information impacted your future studies, be it in high school or beyond? And would you think twice about bringing electronics into your home now?
How it impacted me personally? Like I didn't know any hardware stuff before this course, and then like starting the course, we learned about embedded system. I got confused like right in the beginning when we were like discussing what an embedded system is. Something like big I learned was about memory. Like it got drilled into my brain, like stacks, how memories like work in C. So that was really cool. Assuming that I'm gonna work in STEM, these tech skills and certain like programming skills that we learned in this course would be really beneficial in the things I'm gonna do in the future. Would I think twice about electronics in my home? Well, before thinking twice, I think I have to first think once. I usually don't think about electronics like my fan here. Is that gonna get hacked and like start spinning all over the place? Probably not, but maybe. So yeah, I'm probably gonna start like being conscious about the stuff around me.
Where you buy your products from, and you know how security conscious you think those companies are. Yeah, and maybe what data of yours they have access to.
Yeah, it's like pretty scary getting hacked here.
Yeah.
Like I remember like just trying to use the debugger while during the attack phase, and then all of a sudden we got attacked. That was scary but cool at the same time.
Awesome. All right, we're still open for questions. I don't see any additional questions on Slido.
CIA a question.
Yeah, go ahead, Gary.
So I noticed that it looked like they did an RSA signature on each chunk. So what was stopping people from like switching the chunks around?
Someone from CIA want to respond to that?
We actually do have like a chunk order number in the metadata, so the RSA is signed with that. However, I think there is a vulnerability. We don't check the metadata corresponds to all the other chunks every single time outside of the chunk number. So I think you can potentially take, like, say, chunk 0 from another version, put that in, and I think it'll still work. So that was something I thought of when I was doing the presentation.
And also, your presentation was kind of right about the deterrence, because I didn't want to test a firmware against a system that took 2 minutes to upload each firmware.
That's only due to just the ridiculous amount of padding from we have. Like, for every 1,000 bytes, I think there's like 300 to 400 extra bytes of just signature data.
Oh my goodness.
Wait, did you use GCM or CBC?
We use GCM because the metadata isn't encrypted.
GCM doesn't need padding, though.
GCM doesn't, but RSA does.
All right. One more question for BeaverWorks. Oh, I guess this is a question to the instructors. So I guess for all the teams, are you planning on sharing your code, notes, slides on GitHub or another platform? Maybe that's more of a, can you please do that? If, feel free to share your notes and kind of what you learned, your code.
I'm pretty sure our bootloaders are on GitHub, although they might be private.
Okay, we'll sort that out after. All right, so we got 4 more minutes for questions.
I have a question. I think it was the shifters. I might be wrong. In your threat model, you said you identified that hardware attacks like side channel attacks weren't really going to be something you were going to worry about because of the emulated environment. How would you have changed your design if that were something that you were going to include in your threat model?
So I think I can answer this one. So side channel analysis basically collects a bunch of data on like the decryption of the ciphertext, or that's at least differential power analysis, and it then can correlate like the power traces of that data and figure out the keys. One way we went about it is we checked for authenticity using our RSA first, which means that even if they did do a differential power analysis, they would figure out the public key, which wouldn't really help them at all because it's encrypted with a private key, and that's still a secret, and the public key doesn't really matter. It's only to verify that it's really the company that's sending this information. Other than that, I believe we need to do a little bit more research how to obscure the AES encryption, but we were thinking of a key rotation. So that could be something we do in the future if we do potentially do this in a actual like physical setting.
Cool, thanks.
All right, we got time for one last question. 2 minutes.
I'd actually be curious to know some of the other students that, like for the question that Jen answered for Team 3 about how this has changed your outlook on kind of maybe what technical areas you want to learn about, and like your outlook on electronics and security of consumer products. So if anyone wants to share their thoughts on that, that'd be great.
I kind of find it scary, like how important security. Like I already knew that security is really important, but like we pretended we were like coding for cars in this case, and like if someone actually was able to hack into like an actual car we designed, that would be really bad because, well, that could kill someone potentially. So that's really interesting in my opinion.
I was just going to say that I agree with Zawad. Definitely after we had some amazing speakers throughout the session, we would be talking in our Discord server, just saying kind of like how this class has made us a little bit paranoid, just because now we do realize all the different ways that the systems around us can be hacked. But in terms of kind of how this course has changed what I want to do in the future, I've definitely been interested in computer science for a few years now, but I've never done anything with embedded systems, anything like that. I wasn't even sure if I wanted to, but definitely after this, I want to kind of find different ways I can keep learning because it's definitely super cool.
I personally realized that even when the code seems to work and everything seems protected, it can be the hardware that can be your issue. And that really opened my eyes because when I thought computer science, I'd be like, oh yeah, I love programming, it's fun. but I don't really like the electrical side of it. And now I'm realizing that I kind of have to like the electrical side of it, because you can protect the program, but you might not protect the CPU or the computer itself, and you need to be able to work with both.
All right. Thank you, everyone, for sharing answers to that question. I think we're going to head back to, well, actually, I don't know where we're headed next. It's either the main session, or if you'd like to go sit in on the second round of classes who will be doing this same set of presentations for their course, you can go and join there. Other than that, I just want to remind all the students that the scores on the scoreboard are not final. We're tallying up the points as we speak, and we will announce the first, second, and third place winners of the design challenge. So we'll see you this afternoon.